problem for 24 and Vector Statics book edition for 5th edition by Hibbeler. So in this problem you have a beam that has a contact point at the wall at this location. You see that this is just a smooth, frictionless contact point, right? Surface to surface. And then we actually put it on another pin here, but it's not a pin connection, it's just like a slider, right? It's a surface contact point, frictionless again. Now the question is, find this length D, so this unknown, such that this system remains in equilibrium if we apply a force P. So everything is parametric. We don't have the actual value of force or distance, right? So again, in order to solve this problem, we do 5 steps. I'm not going to write it anymore to save time. So my system, the first step is choosing the system. My system is, I choose the beam as my system. So I'm trying to separate it from the surrounding isolated. So this is my system, as you can see. There you go. Now I start walking on this surface to find the surface force, and then I add body force, and then I'm pretty much done with the free body diagram. So I start walking from here. The first thing I cut is this force P, so I have to include it to my free body diagram. So let's use blue to include the external effects. So there is a force P here, and then I continue walking. The next thing I have is this contact point here. As you can see, there is no friction. The only force is normal to this direction, right? There is no tangential component of force because it's frictionless, right? And there is no movement. So the only thing I get is a force acting at this location, and its direction is normal to the system. This force is coming from the outside world, which is that contact point. Let's call it, for example, let's call this point A, and let's call this point B, right? So that's, I call this FA, the unknown force coming from the contact point at location A. Now continue walking on the border. The next thing I can cut is the contact point at location B. Let's call it FB. Again, that's pretty much the same contact, frictionless, except the normal direction would be in the positive X direction. Now continue walking back, and then I'll go back to my start point, and I'm done with the surface forces. Now the body force, according to the question, is say you can ignore the mass of the beam, so there's not going to be any body force. So all I need to know is to find these two unknowns that I have, FA and FB, in the term of P and this length, right, D, and this parameter here is given this distance A. So assuming that I have these things given and this angle is theta, right? This angle is also theta. Assuming that these parameters are given to me, then I want to find this distance D. So I need to get an equation for this D in terms of others, such that if I give this value to me, like if somebody say I apply force 10 kilonewton, right, and the angle is 30 degrees, right, I can be, and this distance A is 2 meters, then I should be able to estimate the length of beam that is required to stay in equilibrium position. This is just one numeric example, but here everything is parameter. We don't have numerical value, right? So we have to solve this equation parametrically. So let's choose black color. Now this is my FVD, and the next thing I do, I go and write the equations. This is one system, right? So I only have 3 equations. Summation of force in x0, that would give me, so if this is theta, this angle is theta, right? So in the x direction, I'm gonna have fa sine theta negative, right? Then the next thing is plus fe is equal to 0. That's my first equation. Second equation, summation of force in y 0, that would give me negative p plus fa cosine theta is equal to 0. And summation of moment on any point is equal to 0. Now, this is the tricky part. What point should I choose as my moment reference, A or B? Obviously, the point that force P is acting on is not a good point, because we assume that P is given to us. So we're trying to find something either A or B, right? So I can choose either one. It doesn't really matter. So what I do, in this case it doesn't matter, because either A or B would eliminate one unknown, right? So there is no advantage over A and B, right? So I choose, in this example, I choose point, let's see, B, okay? I choose point B, and then I go ahead and write, so I say this moment, let's use another color, with respect to point B is equal to 0, right? And then I go ahead and write the equation. So the first thing, the moment coming from this FA is already orthogonal to the surface, right? So it's going to be the distance, which is from here to here, from here to here, right? So what is that distance? Let's call it x. So in this triangle, if I write the equation for cosine theta is equal to a over x, right? So x would be a over cosine theta, right? I consider, let's use another color, I consider this triangle here that I highlighted in green. You see that? So in that triangle, cosine theta is a over x. So this distance x would be a over cosine theta, right? Now that's my moment arm. Now I'm going to be using it when I compute moment about point B, right? So the first thing would be x time FA, right? Positive or negative? Obviously positive. Use your right hand. And the next thing would be this force, decompose it, force P. If you decompose it, you're gonna get a component like that, right? And a component like that, right? This one, you don't get any moment from it because it goes through point B. So the only thing that gives you moment is this guy, right? Which is P sine theta times D. Alternatively, you can move this guy down, right? And at this point, it becomes, we bring it right here. So the moment arm is from here. Let's use another color, hopefully. Moment arm will be from here to here, which is d cosine theta, right? So, excuse me, if this is theta, if this is theta, this component is p, right? Cosine theta is not p sine theta. So using the projection method, you have p cosine theta, the moment is p cosine theta times d, right? Alternatively, if you use method of moving forces, you have to move it right here, right, at this point, and the moment arm is from here to here, as you can see, and this distance is d cosine theta times p. So again you get p cosine theta times d. So that's your moment. So I'm going to be adding it here, and since it's negative, I say negative p cosine theta times d, right? The sign is negative. So that's all the moment. It should be equal to 0. Now this is the step writing equation. Now we go ahead and solve it. So before we solve it, let's assume that theta is given, right, and p is given, and a is given, right? Let's assume that these are all given to me. Now the question is, how many unknowns do I have in these three equations? Well, the first unknown is fa, right? The second unknown, fb. What about the third unknown? Well, theta is given, right? We already considered fa as an unknown. P is given, again fa is given. X, I found the equation right here in terms of a and theta is given, right? P is given. So the last unknown, I'm gonna circle it with red, is d, right? So I have three equations and three unknowns. If I can figure it out for these three unknowns, then I should be able to find the equation for d, which is the answer to this problem, right? So in order to do that, let's first solve for d, and then if I need fa, fb, I can get the value from this equation or this equation and put it back in the d. So according to the last equation, let me check mark this equation 1, 2, 3, right? So I start with equation number 3, solve for d, is going to give you d is equal to x fa over p cosine theta, right? Which is equal to, according to this equation that I'm check marking right here, x is a cosine theta times fa, a cosine theta times fa divided by p cosine theta, right? Now going back to the assumption, assuming that the angle theta and p and a, these are parameters that I know somehow, although they are parameters, but it's a designer choice, right? You can fix them, but fa is not your designer choice. You have to substitute the value from equation either 2 or 1 for fa into the distance d. Now if I look at equation number 2, I can see that I have a equation directly for fa, and it's not even coupled to equation 1. So I can immediately solve equation 2 for fa. So according to equation 2, I'll write it here, equation 2 would give me fa is equal to p over cosine theta. Now let's put it back right here. So you get d is equal to a cosine theta times fa, which is p over cosine theta over p cosine theta. So the final answer would be a over, so this p cancel out with this p, and then you get cosine 2 times cosine theta to the third power. It's a cubic term. So d would be a cosine theta to the third power. Let's write it with another, let's use the eraser here. So d, let's use this, d is equal to a over cosine theta to the third power. Interesting, very beautiful equation. And this is my final solution for this problem.